Okay.
We got it?
Yeah.
Are we recording?
Mm-hmm.
Here we go. So, this is the beginnings of 10G. Growth and decay. Exponential growth and decay. So, let's say that you have some amount of something. Maybe it's money. Maybe it's stores that you own. Maybe it's bacteria in your body. I don't know. But we have some sort of amount. And it is increasing or decreasing. For this case, we'll just say increasing each year. There is a 25% increase. So each year is 25%. And we don't want this to be scary or sad or biological, so we'll just say these are, I don't know, businesses that you happen to manage or own, or that your company, locations of stores, okay, something like that. So the original amount, 200. So you start off with 200 stores nationwide. Let's figure out what that growth looks like. After 1 year, so you start off with your 200 stores, and then you add to it 25% growth. So 200 times 0.25. Yeah, but I'm going to write it all out here so that we can very quickly see what the formula is, see what the pattern is, and then we'll be good to go. So 200 plus 200 times 0.25, or if after I write that 200, I have 1 plus 0.25. We could write that as 200 times 1.25. So. And now I'll take that final answer.
150.
250. So after 1 year, you have 250 stores. Hey, that's great. After 2 years, so you could say at the beginning of that second year, assuming that all the stores were up and built by the end of December and so on and so forth, you're going to have that 250 stores that you have to begin with, plus that 250 times the 0.25. So I'm going to write this, instead of writing though the 250 right here. Well, let's just go ahead and play the game here. All right, so that's what's that number right there? What's the final answer? 250 plus 250 times 0.25. Someone other than Emily here. That's why y'all have calculators. 312. 0.5. Okay, so that's interesting. How many stores did we go up from the time we began till the end of year 1? 50. So it might be like, okay, I'm going up 50 stores every year. Not necessarily, because how many stores did I add during that second year?
62.
Oh. Okay, so that's pretty cool. Okay, great. Thanks. So after 3 years, we're starting off with the 312, and then we're adding 25% of that. So plus 312.5 times 0.25. Somebody new? Go ahead and type those numbers in. Give me a final answer.
390.6.
390.6. Now, 312 plus 312 times 0.25. Now what's the difference? How many stores did we grow?
78.
Oh wow, plus 78. 78.1 I guess?
Yeah.
That one's still in progress. The 1/10 of the store built. Just that little corner over there is already all finished. So we're about the other 90%. So anyway, this is something that is difficult for people to get our minds wrapped around. That if we've got 25% growth every year, okay, I guess maybe it's not hard to get our mind wrapped around it, but the idea is that at the end of that first year, you have more than what you started with, okay? That's obvious. But what's really cool is that if you're able to lock in that 25%, okay, then 25% of whatever you have at the beginning of that second year is going to be more than 25% of what you had at the beginning of the first year. So you're going to be adding more, but the amount that you're adding more is growing. Does that make sense? If we continue on this just one or two more times, we're going to, every year we're going to be getting over 100 and then over 200 more, all right? So let's just do maybe one or two more. So after 4 years, 390.6 plus 390.6 times 0.25. 488.3. What's the change there? Almost 100. Looks like, was that 98? 97.7. 97.7. So. Right. And so I'm pretty sure after 5 years we're gonna, we're gonna have even 100 new stores. Couple of things. We can see that this is growing, but it's not growing, we would say, at a linear rate. It's not growing the same amount every year. It's growing exponentially, okay? It's getting faster and faster and faster. Now, if I'm on the board of trustees, if I'm a stockholder, if I'm the owner of this business, okay, then I am loving this, okay? I started off in year 1 with 200 stores. At the end of 4 years, I've got 488 stores with another one, 1/3 finished, okay? So, I mean, we are getting, crazy growth here. It is hard to maintain that 25% growth if you're talking about a business, in terms of like number of stores and things like that, because you're adding, more and more and more stores every time. But you can have growth in lots of other ways, other than that. And we'll talk later about money and investments, and if you don't just put all your money in one company, but you kind of give your money a little bit to another one company here, and a little bit to this company over here, and a little bit to this company over here, that actually becomes very reasonable. Now, 25%, that is an amazing return. It is possible to get that. I'm shooting more for the 10 to 15% personally, but in businesses, sometimes that's not an issue. Now, let's go ahead and there is a generic formula for this, but I don't think we're able to see it very well. Let's just write it over here.
Compound the interest formula?
It's more of the exponential growth is what, I mean, a compound interest formula is what we're doing, but it relates to exponential because it's an exponential function, okay? So here's, I'll just go and give it to you. You might be able to see how this works. So it's the final amount is equal to the initial amount, which we call the principal, or we spell it PAL, times 1 plus the percentage rate, so that's the rate, and then T is our time. You can start to see that you've got the initial amount, 1 plus the percentage. For this first one, it was just to the first power. We would see that as we extend this out, then After 2 years, it becomes to the power of 2. After 3 years, it's the power of 3. 4 years, it's the power of 4. So on and so forth. So let's see if we get the same answer here. So, so you start off with 200 stores. That's our p-value. 25%, so that would be 0.25 is our R value. After 4 years, so that's our t value. Let's plug it into the formula. The final amount, 200 times 1 plus 0.25 to the 4th. What do y'all get? 48.3? Are you satisfied? So yeah, it matches what we were building over there. I guess I could also say that's a plus if this is growing every year. It's a minus if it's decreasing every year. Thank you, Kevin. Now, in this particular example, our stores were growing, you know, planting new stores, starting new branches, and so on and so forth. Every year, at the end of every year, we said, okay, this is what happened. It is possible that maybe we're talking about bacteria growth, and bacteria doesn't wait a whole year till it finally grows some more. It might wait maybe a couple of hours, or maybe a couple of days before it reproduces or something like that. And so that time period is, we say that's the time that it takes to compound, for it to, you know, reproduce or to build upon itself, for it to grow. So I'm going to say this is it's not the time to compound, but this is more specifically, it's the number of times that it's been compounded. In this particular example, it was compounded once every year, so when we said 4 years, then that was 4 compounding periods. We'll look and see some variations on that here in a little bit. All right, let's talk. It depends which word I say here. Might get different responses. Let's talk chemistry. All right, okay. Let's talk physics. Oh, okay. Let's talk radioactive decay. That's actually both. Okay, all right. So, well, that should be the scariest thing. Okay. One of the things that you have in chemistry, and in the physics side of chemistry, particularly with radioactive substances, is that they will decay. And let's talk video games. Yeah. Okay. Let's talk half-life. All right. So you're like, I don't know what that means. Okay.
Well, the third one.
Poor joke.
All right. So half-life is how long it takes for half of a substance to decay. So let's say you've got some sort of radioactive metal type thing, something like plutonium or uranium or whatever, and it's got so much energy, it's moving around, stuff like that, and some of those particles will just randomly kind of shoot out, and they're emitting energy. You know, they're turning it, actually the mass is turning into energy and stuff like that. And so it's, if you sit there and watch it long enough, then it'll like slowly disappear. Okay, but you might have to wait like a couple million years for the whole thing to disappear. But if you measure it, say, okay, right now there's 1 kilogram of it, and then you click your stopwatch, and then a little bit while later you measure there's only half a kilogram of it. You put your stopwatch and say, how long did that take? And that time is the half-life. How long did it take for half of that amount to decay into energy or whatever? So half-life is the time it takes for half of a material to decay. We talked about the half-life of water that's evaporating. Or maybe we could. So, for instance, let's say you've got some uranium, 30 kilograms, and we have a half-life of 100 years. That means it's going to take 100 years for 15 of those kilograms to go away. So we can say after one half-life, let's put, that's actually 15 kilograms. I'll just put 15. Which is the 30 times the 0.5. How much is left then? 50 kilograms. So after 2 years, guess what?
7.
It's all gone. No, it's not all gone. Only half of what's remaining is gone. That kind of sucks like that. I don't know why. So anyway, so after 2 half-lives, half of that 15 is there, so 17.5, or sorry, 7.5. So that's the 30 times the 0.5 times the 0.5. That's how much is around. Or you can think of that. Jasmine, we all right?
Yes.
Okay. You have a question? Okay. So 30, sorry, that's really ugly, times 0.5 squared. Those of you with the calculator, what about after 3 half-lives? How much is going to be left over?
3.75.
I'm hearing 3.75. I'm hearing agreement. So we can think of it as that previous amount, 30 times 0.5 squared. Thank you. Times 0.5, so half of whatever was there previously. So 30 times 0.5 cubed. Anybody seeing a pattern here? So we can say that if the substance decreases by 50% per half-life, the final amount A equals, can you derive the generic formula? Taking all guesses here.
Principal times 1 minus the rate, and then sign.
Okay, well, it's
Times rate.
the rate, which is
50.
50.
0.5.
So 0.5.
Times
And-
rate T.
Well, in this case, the rate is 50%. So it's like we're told that it's we'll get 50% decay. So you could put 1 minus 0.5, but 1 minus 0.5 is
It's the
0.5.
square root of, or to the root of T.
To the power of t. That is correct. Yep, right there. This is sort of a shortcut, quick formula version. You might say, isn't this just the same? Can we just rewrite this as the other one where it was the principal times 1 minus 0.5 to the t, because it was like decreasing every time, like decaying? And the answer is, yeah, you could. Because 1 minus 0.5 is 0.5 to the t, and you're right back there where you were. But this is nice because you're going to see that on a lot of your homework problems. So if you've got half-life,
Oh, but half-life is always 50%.
It's all, yeah, exactly,
Okay.
so.
The principal would be 30 kilograms, so.
Yep. So if you, yep, and so if you wanted to plug that in, you could try it for, plug in 30 and 3 right here for the time and see if you get whatever we had, 3.75. Pretty sure you will. Okay. So we're moving right along. Doesn't take long to go through this stuff. All right. Any questions so far about growth, decay? All right. I'm going to need a lot of number crunching here. So now we're going to specifically talk about compound interest and money. Okay? Because there's some really interesting things that can happen with money.
Wow.
All right. Here we go. It's Monday. Thank you, Esteban. Let's say we've got $1,000. We're going to earn 10% interest. That means it's going to be compounded. We're going to get 10% based on what we put in every year. All right, and what I want us to do is we're gonna plot this for about the first 4 or 5 data points, because then we're gonna make this a little bit more realistic. Okay, so we've got to start with the very first scenario. So here we go. So after 1 year, get $1,000 at 10% interest. What's the interest?
$100.
$100. And so your final amount, $1,100. I guess you could say this is our p-value. This is our R value. This is our year. So I can say that's our time, I guess. So after 2 years, so you started off the second year with $1,100, still at 10%. I think I could do this one, 10% of 1,100. $110. Might be able to do this one in our head here. So let's add $110 to that $1,100. $1,210. So you say, how in the world are you getting this 10%, Mr. Guy? That sounds amazing. Like, what do you do? And I'll tell you, well, one way is I could start a business, and every year I get smarter about my business, and I find new ways of saving money and new ways of getting new customers to come in, and so I'm having more people come in and buy the stuff, and so I'm making more money. Maybe I'm really not that knowledgeable about business, or I've got a full-time job and I don't want to run another business that's going to do me stuff. So what I could do is I've got my friend over here, and she's going to start a business, and she's like, I need some money to start a business. And I'm like, how much you need? She's like, I need $1,000. I said, okay, I'll give you $1,000, but I want 10%, back on my $1,000. If you make a whole lot more money than that, that's whatever, that's yours. But I'd like 10% on my initial money that I gave you. And she says, okay, that's great. And so she goes and starts her business, okay? At the end of the year, she gives me back 10% of that initial amount that I gave. Now I still have that $1,000 invested, and so I might say, okay, you know what? I'm gonna give you that $100 back. So now you have $1,100 of my money, sort of in your business. Go ahead and do some more stuff. You seem to know what you're doing. I just want 10% back on whatever my investment is. And she says, okay. And she goes and does some stuff, and she gives me at the end of the second year, she gives me $1,210 back. Now here's the thing: if she's a business owner and she's making crazy money, she gets to keep all the rest of the stuff. She has to give back to me, whatever I gave her plus that 10%. Okay. Now, I don't really know any amazing, personally, any women that have their own business and have offered me investment opportunities. Okay, not yet. Okay, but what I do know is I do know some like banks and companies and stuff like that say, hey, if you give us your money, we will go and spread it out to all these other businesses, and as they make money, they'll keep some of it, but then they're going to give back a certain percentage of their profits to you. And so that's how I do it. I don't like having all my money in one place. Kind of risk averse in like that way. But you can always kind of spread it all out. Anyway, we'll talk more about that. We'll talk about mutual funds. We'll talk a little bit about more how you can kind of get this 10%. But all sorts of different ways. I don't want to lock you into, one particular way. Here we go. Year 3. Starting off $1,210 at 10%. 121. So at the end of that year, I have
1331.
1331. We're going to start getting into the decimals here. That's all right. After 4 years, I start off with 1331. 133.1. Say it again.
1464.1. Yep.
All right. Good job, everybody. Good job for whoever's making this 10% for us. Okay. Once again, notice we can see that the interest payments that we're getting each year are going up, and they're going up by an increasing amount. They got $100, they got $110, they got $121, then $133. Okay. So this is what we would say if your money is getting compounded annually. Okay. Now here's the thing. Most businesses do not compound annually. So they do something called semi-annually, well, no, most of it's quarterly. So we'll do that for a second. Let's go ahead and fast forward, use our formula here. I want 10 years, 20 years, and 30 years, okay? So 10 years, we'll say A equals the principal, so 1,000 times 1 plus 0.1 for 10. 20, that's going to be 1,000, 1 plus 0.1 with 20 as the exponent. And 30, that's 1,000, 1 plus 0.1, 30. Go ahead and record those numbers, or you can use a table if you want to. All right, anybody have the 10-year number?
2,593.7.
Somebody else? The 20-year?
6,727.5.
Man, $6,000. Just start off with 1,000. It's not bad. I'm just let somebody else do the work here. Whoa, 17,449.4. Even more amazing. Okay. So that's a way. I just have $1,000 plus a friend who knows how to run a business and promises to give me 10% every year. I don't have to do anything. I just got my regular job, and my $1,000 after 30 years is now $17,000. Okay, not a bad deal, right? Okay. So, like I said, most companies or businesses don't do this just on an annual basis. Instead, what they do is they'll pay that interest back semi-annually. So it's not going to be once every year. They're going to pay you twice every year. Sound good? Better, right? I mean, would you rather?
Getting the same amount?
No, we're not.
You're getting less.
Well, the thing is they're not going to give you that 10% every year. They're going to give you 5% after 6 months, and they're going to give you another 5% at the end. Now you're like, okay, well, isn't it going to end up equaling the same thing? The answer is actually no. All right, so let me show you. You start off with the $1,000, okay? And after 6 months, 5%. That's going to be $50? Okay, so after 6 months I have $1,050. Reinvest that, so $1,050 at 5%. So what's 5% of 1050? That doesn't sound right. It should be 52.5. So 52.5 plus 1050 is $1,102.50. Yeah. So this is compounded, what we say, semi-annually. At 5% each term. How much did I make in the other year? Or the other? 1,100.
So you made $2.
Exactly. So this turned out to be better for me as the investor. Yep. Pretty good. So you're like, okay, is there a formula for this? Yes. There is. We would say, so my final amount is the principal 1 plus, and then the rate was cut in half here. So rate divided by 2. And then I've been putting t here for the number of years. Like if I put if t is years, then I would put t times 2, where t is number of years. Okay, so we could run the numbers and all that. Here in a second, we're just going to table all of this. We're going to make a table. We're not going to put it on the table and push it aside. All right, but what's even more, most semi-annually, honestly, I don't know if I see semi-annually very often. What I mostly see is quarterly. Okay, businesses, you hear about the quarterly reports in the news. When y'all read the business news and things like that. So quarterly, the quarterly earnings report came out. And that's when they pay all their shareholders and things like that. So formula is very similar. They pay you 4 times a year rather than 1 time or rather than 2 times. However, they don't give you that annual, big 10%. They take that annual and they would divide that by 4. And the exponent here would be t times 4, where t, of course, is the number of years. I don't know if I want to ask this. Do y'all, anybody have a friend that has a credit card? Maybe some of you, parents, okay? I'm not going to, you have a credit card, I don't know if I want to know that. Credit card companies, they kind of are on the other side. That's the one where you owe them the money. All right? Does anybody know how often credit cards will compound? Monthly, yeah.
Oh my God.
All right, so it's good. Remember, the more you compound, it's better for the investor. It's better for the loaner, right? Not the borrower. Okay, it's better for the lender if you compound more frequently. So that means it's worse for the lender. So for credit cards, the formula that they're using is 1 plus r over 12. So you're like, well, it's not like they're multiplying it by that same percentage. It's 1/12 of that annual percentage, but then you multiply that exponent times 12. So this leads us to the most generic formula, okay? And that is this. So this is monthly. The most generic compound interest formula, A equals P times 1 plus R over N to the N T. All right, where N is the number of times that it's compounded per year. So it's compounded twice per year, we divided it by 2. When it was compounded 4 times a year, we divided by 4. Monthly, divided by 12. And then T is the number of years. All right, so what I want us to build is, very quickly with our calculator, let's go ahead and go annually, quarterly, and monthly. And let's plug that into the y equals on our calculator.
Why do you want us to do that? With what numbers?
I'll show you. With the ones that we've been given. So let's see. It doesn't like that. So y equals, so we'll say 1,000 times 1 plus 0.1 to the x. I could say 1 times x, that's the same. So that's annual. Then we'll do quarterly. So 1,000, 1 plus 0.1 divided by 4. Oh, 0.025, yeah, that's 100%. 0.025. And then raised to the power, I'll put this in parentheses, 4x. And then we'll try this monthly. So 1,000, 1 plus, I'm not going to do all the calculations myself, let the calculator take care of this. So I'll say 0.1 divided by 12.
You have to put that in parentheses.
PEMDAS says no. To the power 12x. So we've got annually 1,000, 1 plus 0.1 to the x. Quarterly 1,000, 1 plus 0.025 to the 4x, and monthly 1,000, 1 plus 0.1 divided by 12 to the 12x. Let's go and look at that table. Alright, Jasmine. What are you noticing about y1 versus y2 versus y3? Y3 is more? Okay. Let me walk around and show me those tables here, folks. I'll go back. lender, is it better monthly, quarterly, or annually?
Monthly.
Is it like a ton better?
At first, no, but as time progresses, yeah.
Yeah, it gets better. Alright, now here's something that I want you to see. Notice, it's really clear on this first line, then we gotta go. So, we're going up by an extra $3, right? Okay, we're multiplying 3 times as often, right? Okay, or actually 4 times as often. We're getting an extra $3. Then we can multiply by 12 times as often, and we barely get an extra $1.
Wait, but this is because this is when it's compounded like the first, so you're comparing it pretty much a whole year to 1 month, isn't it?
Yeah, it is. Well, but then but the thing is that it's the change from annually to quarterly is more than the change from quarterly to monthly.
Oh.
Okay. What we'll do is we'll look at those graphs here. Look real quick. I'll tell you this. We don't have to graph all this stuff next time. Here's what those graphs look like, folks. All right, that is annually. Hold on, I need y'all to just stop what you're doing and pay attention to this. This is super important. So here's annually. Here's once a year. If we do this quarterly, it goes up faster. Okay, so we definitely have a shift. If we go monthly, okay, it goes up even faster. However, the shift is not so much.
Wow.
Hold up.
Let's do that again. No.
We're not doing that. You might say, what about if I did this every day? What if I compounded every day? Would it be even better for the lender? And the answer is yes. But not as much. Okay? So we are increasing the amount, but that amount that we're increasing is getting less and less. So it actually eventually approaches a very fixed value. Even if you were to compound every minute or every second or every nanosecond, we're continuously compounding. All right? And that's what we'll talk about on Wednesday. Be ready for that quiz tomorrow. See you then.